So these are contents, why we study generative models, and there are three major deep generative models, VAE, GAN, and diffusion. Today we will study the first two, why we study generative models, and variation autoencoder, VAE. So there are two types of training strategies. The first one is supervised learning. Supervised learning, assume we have fully paired data. We have input X data, and it's labeled Y, and the goal is learning a function to map X to Y, right? X is input, Y is output, and then we'd like to train a function which can take input X and output Y. There can be many examples, right? Just classification, take input image and then output class of that image, and then image captioning from image, we can output some text description of that image, or detection is a combination of localization and classification. We localize the object and then classify the detected localized object. Or semantic segmentation, we also learned this per pixel classification, right? Per pixel classification. So such kind of detection, segmentation, such kind of thing belongs to supervised learning. We assume we have data and these are labeled Y, and then we just train a function to map X to Y. Of course, they are unsupervised learning. So the difference is that there's no label. We use just data without labels. And the goal is, of course, I mean, as there's no labels, we can't learn a function to map X to Y, right? So we learn a hidden structure in data. We'd like to learn some hidden structure in data, like a clustering, dimensionality reduction, density estimation. For example, K-means is one of the famous clustering algorithms. From data, let's say we have data. We do not have label, right? We only have data. And then we'd like to cluster data, right? So maybe this cluster belongs to dog image, this cluster belongs to cat image, this cluster belongs to human image. As there is no label, we can't do supervised learning, but even with only data, we can do this kind of stuff, trying to get hidden structure of data. And PCA, principal component analysis, it tries to reduce the dimension of data, right? Just maximizing variance of each data, getting an axis that maximizes variance of data, and then keep projecting data to such axis. That is the PCA, one of unsupervised learning. And density estimation from lots of data point. We'd like to approximate it like a Gaussian, fitting Gaussian distributions to data. Such kind of density estimation can be also unsupervised learning. So the goal is learn hidden data structure. I mean, let's say we have lots of point data, and then we'd like to fit Gaussian distribution to the data, or we'd like to reduce dimension of data, we'd like to cluster data. So learn hidden structure of data. And this, as I said, as we do not have labels, it is impossible to learn a function that takes input X to Y. It is not possible. And so far we studied the difference between supervised and unsupervised learning. And let's proceed to generative models. So the supervised unsupervised learning, that is strategy for learning, strategy for training some neural net, some systems. And generative and descriptive model, their goal is very different. So descriptive model, like let's take an example of classification. So classification, take an image data X and then output label Y, right? And the output looks like this. So this is conditional probability, right? Conditional probability. Given input image, what is the probability of this image belongs to cat class? Given this input image, what is the probability of this image belongs to the dog class? Obviously, this picture belongs to cat class, right? So the probability might be 0.9 and 0.1, maybe. This is the discriminative approach. Or we can pass another image, right? Just a dog image, and then maybe this dog image has 0.8, 0.2. So as you can see, there can be possible labels. Let's say we have predefined labels, and then possible labels for each image compete for probability. what does it mean is that we have, I mean, the summation of probability is always 1, right? So the probability of being cat, probability of being dog is fighting each other, and then they competing each other and then because they have a constraint to have a summation to 1, right? So if this goes to high and if this goes to low, right? If this goes to high and this goes to low, so they're fighting each other in the class label space, but no competition between images, right? So this kind of competition is done in label space, right? Given image, given the same image, the probability of this image belongs to cat class, dog class, should be summed to 1, right? So we have constraint so that there is a competition in label space. That is the discriminative approach. But the problem is that let's say we pass just arbitrary image. I'm not sure what this image represents, but let's say we pass this image to some classification network. There's actually no way to handle unreasonable inputs, right? Must give a label distribution for all possible inputs. For some reason, maybe our classifier gives the probability of dog from this image like 0.8 and 0.2, right? So according to our classifier, this image belongs to dog class, but this doesn't make sense, right? We know that this image is not dog. So why this happened? The reason why this happened is that the competition is done in label space. So there's no way to handle unreasonable inputs. Must give a label distribution for all inputs, right? So that is the problem. Generative model is actually opposite. So all possible images compete for probability mass. This is unconditional unconditional generative models. So you can see there is only prior, right? There is no conditional stuff. So the output, this number is like how realistic this image, maybe the number that we can get from this likelihood is that prior is that how realistic this image, how close this image to the real world image distribution. As you can see, this image has very low number, right? This image has a reasonably high number. The reason is that this image, I'm not sure, this image actually a little bit far from what we often see, right? What we often see. So that means this image is a little bit far from real images. So all images compete for probability mass. That is the difference. And mathematically actually very clear. The discriminative approach, the condition, what we interested in is label y given x, right? Y is label, where y is label, x is image, right? Given image, what is the probability of this image belongs to some specific label? That is our interest in discriminative model. But here, generative model, it tries to get, in other words, it tries to get distribution of label space. Distribution of label. That is the interest of discriminative model. Given data, this is data, image is data, given data, discriminative model tries to get distribution of label. That is role of discriminative models. But here, the focus of generative model is not label. It is distribution of data. Distribution of data. Right? Mathematically, very clear. So it is interested in Py, x. Here is Px, where x is data, y is label, right? So generative model is interested in distribution of data. So that is the reason why this image might get some low number. This image is a little bit far from real world images, right? So, but these images, realistic. We often can see this kind of images, while this image we cannot see. We cannot see this image, right? So that is the difference. What discriminative is interested in is label distribution, while generative model interested in is data distribution. That is difference. And actually, generative model requires deep understanding. Is a dog more likely to sit or stand? Three-legged dog more likely than a three-armed monkey. It's very difficult actually. Very difficult to properly training generative models. I mean, how can we determine a dog more likely to sit or stand? Or you need to understand the semantic structure of dog, three-legged dog, three-armed monkey. What is the more likely image in the real-world distribution? This such kind of thing. Many things can happen, right? So properly designing generative model is very challenging. And so based on this kind of generative model, we can reject unreasonable inputs by giving the small probability mass, right? We can, that is actually called anomaly detection. Anomaly detection. Anomaly is opposite word of normal. Something not normal is abnormal. This kind of thing is abnormal, right? Abnormal. So we can, if we have generative model, then we can get likelihood of all data, and then for data whose likelihood is very low, then we can reject such kind of data. As we can say that such kind of data is not does not belongs to some normal distribution. So that we can reject unreasonable inputs by giving the small probability mass. And conditional generative model, basically the same. So the generative model, as I said, is interested in px. Here we have, and here discriminative, this gen pyx, where x data, y label. And here, still interested in px, data distribution, a condition on label. So given cat, given label cat, this image belongs to, has high likelihood, right? This image has low likelihood. Given dog, this image has high likelihood. This image low likelihood. So these are very different. P, y by x, px, px by y. Each possible data label induces a competition across all possible images. So that this is the typical thing that we can use these days, like image generative model, video generative model. We give text, right? We give text as a y text, and then x image video, right? So conditional generative model is what we typically use these days, giving a text or any condition as an input, and then the model can randomly sample some images or videos whose likelihood is high. That is the role of generative model. So, in summary, descriptive model is interested in label space, py by x, given input x, given data x. The focus is on label space, and then generative model focuses in data space, x, where we can introduce additional conditional generative model, which is conditional label, but still interested in data distribution x. So that descriptive models cannot handle any unreasonable inputs, but on generative model, as we can get likelihood of all images, then we can reject some unreasonable images by giving them low likelihood. And this is Bayes rule, and then this is very governing equation in machine learning, and the Bayes rule shows everything actually about descriptive model and generative model. So px is generative model, about generative model. Unconditional prior. This is also called prior. So prior means something. Prior. What does prior means? Prior is actually before something, right? Before something. What? So what's something? Before observation, actually. Before observation. Before observing something, observation is y. Y is observation. Before observing something, we have some basic knowledge about the world, right? Maybe there are about 50-50 men and women on this planet, right? Such kind of thing. In some places, maybe there can be many more guys, there can be more women in some places, but on average, on our planet, there can be 50-50 men and women, right? Such kind of thing. Before seeing something, we have some knowledge about the world. That is prior. This is prior. Before observing something. And descriptive model is interested in this one. Without prior, it only interested in likelihood. This is likelihood. Likelihood. And this is posterior. So posterior means after something. So something is also observation. After seeing something, that means after observing something, our probably changes to from prior to posterior. So this is called prior. Generative model, unconditional generative model is interested in, and this one posterior, where conditional generative model is interested in. And the difference is that whether we have observation or not. If we do not have observation, then prior. Prior means before something. Before observing something, we have some knowledge about our world, right? And then that is about prior, before observing something. But let's say we observe something, observe this classroom or observe any images, then situation might depends on each cases, right? That is about posterior. If we have observation, then our prior is changed according to the observation. That is posterior. And likelihood, it is different from prior. Given data X, it is tried to get label right. That is about descriptive model, while posterior and prior distribution are the main focus of generative model. Unconditional prior distribution, that is the unconditional generative model. Posterior, it is about conditional generative model. And so the descriptive model, we can assign labels to data. And then generative model, we can detect outliers. As I said, this is anomaly detection. We can give, some unreasonable data might have low likelihood, and then we can reject such kind of data. And then the important thing is a sample. We will learn this. Also, we can assign labels while rejecting outliers, sample to generate data from label. And here, generative models, generative model means either of these conditional generative models are most in common practice. As I said, this one. Maybe in some cases, we can just randomly sample without any text prompt, right? But in many cases, we give some text prompt, and then we sample something, generate some dog image, generate some cat image, and then based on the text prompt, the model to sample something from data distribution, not label distribution. That is important. If model is sampling from data distribution, that is generative model. If model is something on label space, that is about descriptive model. So label space, and this one data space. Actually, there can be many ambiguities, especially if you're interested in generative model. Like, given a single input, like a single text prompt, there can be many possible outcomes, right? For example, write me a short rhythmic poem about generative models, then there can be many poems, right? There can be many outputs. Or text to image, right? Text to image also. Given text prompt, there can be many possible images, right? Or video as well. Image to video, if we have image, and then there can be many possible videos, right? There can be many possible videos. So that is ambiguity. But on generative model, actually can handle such kind of ambiguity properly by randomly sampling data from learn px. So here we also learn sample, right? Sample. Sample means, let's say we have this kind of normal Gaussian distribution, and then maybe if we randomly sample something, then this is likelihood. So we can maybe samples around this one. This one has high likelihood. Maybe we can get data from randomly sample from this one. So for every sample, we can get different outputs as we have distribution of learned P. We have learned P, right? Generative model provides distribution of Px or Px by y. And then from this one, we can randomly sample, not just simply estimate a single output. I mean, generative model often estimate distribution, and then from distribution, we can randomly sample some data. Let's take an example. This one. Sample means, for example, this one. Let's say we have this distribution. X1, X2, X3, X4. This is very simplified version of image distribution, but let's say there are only 4 images on our planet, and then X1 image, cat image has some maybe 0.2, 0.4, 0.2, no, 3, 0.1 maybe. Let's say we have this kind of distribution. Only 4 images exist on our planet, then maybe for every random sampling, maybe this image has the highest probability, so we can get this image most often, right? Let's say we have the data distribution. We have this kind of table distribution. X1, X2, X3, X4, and then 0.2, 0.4, 0.3, 0.1. That is a distribution, very simplified version of distribution. From this distribution, we can randomly sample some image according to these numbers, right? As this image is highest probability, for every random sampling, we might get this image most often. So this is what generative model provides us. Distribution of data, not label, data. And then there are taxonomic generative models. The first one is model can compute Px. Px is, we learned this one, right? Prior distribution. And cannot compute Px, but can sample from Px. That is explicit density and implicit density. And if the model really computes Px, then tractable density, autoregressive model belongs to this class, and approximate Px. So approximate density, that is variation autoencoder, and GAN can directly sample from Px. And iteratively procedure to approximate samples from Px, indirect diffusion model. So we will today learn variation autoencoder today, and then next time we will learn GAN and diffusion models. So it's very important to understand what Px means actually. Px, as I said, is a prior distribution without observation. And then actually computing Px, it belongs to autoregressive model. It's a little bit theoretic, so I excluded this in this course. Approximate Px. Px means, how much likely this image belongs to real world image. That is the Px, right? If this image looks like real dog image or cat image, then this randomly sampled one might have high Px, or images is full of noise, then Px might be very low. So it's a distribution of real world data space. And let's go to VAE. Before going to VAE, is it okay? Anything is unclear? Okay. I'm not sure it's the first time to study generative model, descriptive model. Have you studied this one in other courses? Are you familiar with this one? Not at all? 배웠어요? And before going to variation autoencoder, let's go to autoencoder first. So this is not non-variational version of just autoencoder. So the idea is unsupervised method for learning to extract feature Z from input X without labels. Feature should extract useful information, object identity, appearance, scene type that can be used for downstream tasks. So input is X, and then we have encoder and feature or latent feature, latent vector. And encoder might have any architecture. That is not very important. Encoder can be MLP, standard transformer, anything. But the non-variation autoencoder, it starts with encoder, which encode input data to feature Z. But here we take unsupervised learning strategy, unsupervised learning. So without labels, we simply reconstruct input image, input data using decoder. And auto-encoding means, auto means itself. Auto means itself. Automatic telling machine or automobile, that is also belongs to itself. Automobile. And so solution is reconstruct input image, input data with a decoder. Decoder also can be any architecture, MLP, standard transform, anything. That is not important. And here loss function is, so we do not have any labels. We just use raw data. And then we can just train encoder and decoder with loss function, minimize reconstruction loss function, L2 loss function between reconstruct input data and input data. And maybe we can use autoencoder for the feature extractor. After training, we can remove decoder, and then we just take encoder to get some features, and then use these kind of features for classification. The good thing is that if we have very limited amount of training data, let's say we have lots of x, but small x, y pairs, then we can choose this approach. We have lots of x, so that we can pre-train a feature extractor encoder with lots of x, because training autoencoder, it does not require any labels, right? So we can utilize lots of image data to pre-train encoder and decoder, so that and then we can remove decoder, and then we can use small amount of xy pairs to, maybe we can freeze the encoder or fine-tune encoder, and then we can train very shallow classifier based on pre-trained encoder features, right? That is the one way we can choose if we have very limited amount of data. But we have limited amount of pair data, or if we have lots of unlabeled data, then we can choose this approach. We can pre-train encoder, decoder, and then we can get rid of decoder, and then we can simply fine-tune and train classifier from scratch using small pairs of x and y pairs. And then if we can generate new latent feature, then we can use decoder to generate images, right? That is obvious, because in training stage, given Z, the decoder is trained to reconstruct the input image, right? So if we have Z, if we can generate new Z, then we can use decoder to generate images. But problem is that generating new Z is not easier than generating new X. How can we generate Z without X? Without encoder. How can we generate new Z? That is problem. So one possible solution for this problem is maybe we can force all Z to come from non-distribution, for example, Gaussian distribution, and that is actually where VAE comes from. If we, from this pre-trained decoder, this latent Z can follow any distribution, so we can generate latent feature Z. How can we generate? It can take any arbitrary numbers, right? But if we can make this one follow non-distribution, like a normal Gaussian distribution, then we can sample latent Z from normal Gaussian distribution, and then use pre-trained decoder to generate image, right? That is VAEs comes from. So from autoencoder, we take a probabilistic spin, learn latent feature Z from raw data. That is the same as the non-variation autoencoder. But we sample from the model to generate new data. And then, so assume training data is available, generated from unobserved latent representation Z. Intuition is that X is image, and Z is latent factors used to generate X. Z is latent factor used to generate X, where Z can be attribute, orientation, anything, some latent feature that describe input image X. So if we can make Z follow some known distribution, for example, normal Gaussian distribution, then we can randomly sample Z from normal Gaussian distribution after training, and then we can use those kind of randomly sample Z to recover image using pre-trained decoder. Here's decoder, right? Decoder. As I said, the motivation of variation autoencoder is making Z follow our known distribution, like a normal Gaussian distribution. So this one we can assume simple prior PZ Gaussian. From normal Gaussian, we can just randomly sample, right? And here, sample from conditional P theta is the Lerner parameter X and Z. So how can we train such kind of decoder? Decoder. The basic idea is maximum likelihood. I mean, this probability means likelihood. This is likelihood. So X is observation. X is label, right? In this case, Z is not observed. X is observed. So this is likelihood. And then all we want to get is, all we want to maximize is given latent feature of some image Z, we like to maximize probability where we can get, the probability from condition on latent Z should be highest at the point of image X. That is what we want, right? So we'd like to maximize this likelihood, and basically there's maximum likelihood when training decoder. If we had a data set of X and Z, then we can train conditional generative models, X and Z. Let's say we have Gaussian distribution, right? And then let's say this is from Z. Z. And then decoder. And then it might output maybe roughly same mu and sigma that describe normal Gaussian distribution. And then at point X is at the mean position, right? So that it has highest probability. So when Z is passed to the decoder, then the probability of the output distribution at the point X should be highest, right? That is our goal. That is actually, in one word, maximum likelihood, maximizing likelihood, given latent feature Z, and then we'd like to maximize likelihood at the point of X. That is the goal of training decoder. We do not have observation for Z. Z is latent feature, so we do not have observation. So marginalize this. We'd like to marginalize this. This is just joint distribution, and then we can just marginalize this by decomposing them to conditional and prior distribution. This one, okay, we can compute this with decoder, right? This one is decoder. And then PZ, we also assume that Z is following Gaussian distribution, right? Normal Gaussian distribution. So we know both this one, we know both things. This one is decoder, this one is decoder, and this one is normal Gaussian distribution, right? We all know this. The problem is that we can't integrate for all Z. We cannot, there can be many Z. Z is just a random vector in normal Gaussian distribution. So we cannot integrate over all Z, all possible Z. And another idea is trying Bayesian rule. We can compute this one. Also, we can compute this with the decoder. And then this one, as I said, is from normal Gaussian distribution. But this one, normalizing factor, we cannot compute this one. And that is the, that here we have cell encoder. Train another encoder that learns this one. That approximate this normalizing factor using encoder. So this one shows this one. So we have decoder and encoder. Encoder is, as you can see, there is the approximation function Q. And as you can see from this one, this is encoder. And this is decoder. And this is normal Gaussian distribution. So encoder network takes a input data X and output distribution over latent code Z. And then from sample Z, and then we can sample. sample Z, we can reconstruct input data using decoder. Input is latent code Z, and output distribution over data X. And then we can train both the encoder and decoder jointly. So, I mean, here in the training stage, as you can see, we do not have any labels. We do not require any labels. We have just input image X, that's all. Nothing in addition to input data is used, right? Just giving X data, X to the encoder, and then it estimate the normalizing factor, this one. And then we sample Z, and then from sample Z, we'd like to reconstruct input data, right? And then we can jointly train encoder and decoder. So from this picture, we can guess which loss function that we need to use, right? There should be two loss functions. The first one is, so to make this latent Z include informative attribute of input image. I mean, this one should identical to this input image, right? So the loss function one, casually saying, reconstruction loss. Loss distance output X, right? To make latent Z include informative attribute about the input image X, we need to introduce reconstruction loss, right? And the second one is the motivation of VAE. We'd like to make this latent feature follow some non-distribution, right? Non-distribution. We can use many, we know many distributions. We know Gaussian distribution, we know Bernoulli distribution, we know many distributions, but people just choose Gaussian distribution because it's applicable to many cases. So in VAE also, we'd like to choose Gaussian distribution as the underlying distribution of latent space. And then, so that the second loss function we need to take is making Z follow normal Gaussian distribution, right? That is the motivation of VAE. We learned autoencoder, but it was not enough because we cannot generate latent feature Z. We wanted to make Z follow some non-distribution like a normal Gaussian distribution. So that was the motivation of VAE from autoencoder, non-variation autoencoder. And the first one is reconstruction loss. That is also, applicable in non-variation autoencoder, right? Just without any variational stuff. To make this latent feature Z, include some essential necessary information about input data X, we need to introduce reconstruction loss, right? So there are two loss functions. And from this one Bayesian rule, we can understand that this one is encoder, this one is prior of latent Z that we'd like to introduce in our latent space, and then the left one is decoder. And then one tricky thing is that we from neural network maybe we can output something, but how can we output probability distribution from neural network? It is a little bit practical question. How can we? Maybe we can output probability for classification. We can maybe output some location of object for detection, but how can we output distribution from network? To this end, the network encoder outputs mu and sigma, mean and covariance of Gaussian distribution, and then from this one we can introduce some parameterization trick to sample Z from estimated mu and sigma sample, and this is also differentiable. So that gradient is differentiable sample, so that gradient from this reconstruction loss can be backpropagate to the encoder side, right? And one interesting thing is that, so at the first time we try to maximize likelihood, right? We learn maximize likelihood. Where is maximize likelihood? Maximize likelihood from decoder, right? That is the basic idea for training variation autoencoder. But it turns out that maximizing likelihood, so in Gaussian distribution, we are interested in Gaussian distribution. And this is the logarithm type of Gaussian distribution. And then maximizing, how can we maximize this? By minimizing this one, right? How can we maximize this one? We can minimize this one. Minimizing this one means making sampled mu and x as close as possible, right? That is reconstruction loss. It's very interesting. Maximizing likelihood. The basic idea for training variational autoencoder was maximizing likelihood. That is about reconstruction loss. But it turns out that in Gaussian distribution, naturally, maximizing likelihood is equivalent to minimizing L2 distance between x and network output y, mathematically, right? So that is about the reconstruction loss that we need to use when training variational autoencoder. And it turns out that maximizing likelihood mathematically are equivalent to minimizing L2 distance between input data and reconstructed data. And then, but this is not the only one. As I said, the motivation of variational autoencoder was, constraining, making the latent space follow normal distribution, right? Normal Gaussian distribution. Without such kind of constraint, we cannot easily generate latent feature Z, right? In autoencoder, non-variational autoencoder case, we cannot generate latent features. So that in the variational autoencoder, we'd like to generate latent feature from nonce distribution such as Gaussian distribution. But how can we enforce it? That is, should be included in loss function, right? This is the first recon loss function. But how can we introduce another loss function that can make latent feature follow normal Gaussian distribution? That should be additionally included in loss function, right? So let's get back to Bayesian rule. And then we'd like to learn elbow. Elbow is a short word of evidence lower bound. So we get back to Bayesian rule and then do some simple math, and then do some simple math, and then PX is independent of Z, right? So we can just take expectation for Z, and the expectation of this one means expectation of this one, and then we can separate expectation for each term, right? So that we can take expectation for each separate term, right? So this is just some simple math from Bayesian rule, and then we can wrap in expectation since it doesn't depend on Z. It doesn't depend on Z, right? This one doesn't depend on Z. And then finally we reach to this point. This one, what does this mean? It is about maximizing likelihood, right? Maximizing likelihood. And this one is, Ka divergence is some metric that measure distance between distribution. How two distributions are close or not. How much two distributions are close. That is about Ka divergence. So we have one term about the likelihood and two terms about Ka divergence. This is data as I said, this is data reconstruction. Maximizing likelihood. So that is the first loss function that we need to introduce when training VAE. X is equal to encoder and decoder and should reconstruct as X and can compute in closed form for Gaussians, right? As we learned in Gaussian, maximizing likelihood is the equivalent to the minimizing L2 distance between input data and reconstructed output, right? So that is about reconstruction loss function. Let's interpret this. Let's say we have latent feature Z, latent code Z, and then we can reconstruct it using decoder. We can reconstruct the data, right? And then given Z, we'd like to maximize likelihood at the position of X, because what we want is recovering X, right, from latent Z. So that this is maximizing likelihood, and then that is the data reconstruction loss. First one is data reconstruction loss in VAE training. And the second one is prior. That is actually what we wanted. What we wanted to make latent space of VAE follow normal Gaussian distribution. That is what we wanted. The motivation of VAE was from autoencoder, non-variation autoencoder, as I said. We wanted to make latent feature Z follow normal Gaussian distribution. How can we enforce this? Mathematically, it turns out that from Bayesian rule, we do some simple math, and mathematically we found that, calculating K divergence between encoder's output, this is encoder's output, right? Encoder's output and non-distribution, normal Gaussian distribution, we can do this. So that, we can simply make output of encoder should be matched with the normal Gaussian distribution. That's all. That is the second loss function. Encoder output should match prior over Z. Can compute in closed form for Gaussian. We are interested in Gaussian, right? So we wanted to, so from encoder side, we want this one follow normal Gaussian distribution. That is the second loss function. The first loss function is reconstruction loss function that maximize likelihood from decoder's output, right? Decoder's output is, reconstructed data, and then we simply tries to minimize L2 distance between decoder's output and then input data. That is about maximizing likelihood. That is the first loss function. The second loss function is K divergence between encoder's output. This is decoder's output. This is encoder's output. Encoder's output should match with our desired distribution, normal Gaussian distribution. That is the second loss function. By just calculating K divergence between KL divergence between encoder's output distribution and our desired normal Gaussian distribution. That is the second one. And third one is actually impossible, unfortunately. It's posterior approximation. Encoder output should match PZX, but we cannot get PZX, right? As we do not know PZX, we introduce QZX in encoder side. We cannot get PZX. That is decoder side. From decoder, we can get PXZ, and then this encoder side, QZX, and then this is prior normal Gaussian distribution. Or PZX, real data distribution of latent Z condition on X. We cannot get this, unfortunately. And that is the reason why we introduce encoder to approximate PZ with encoder. Unfortunately, it is impossible to accurately get PZX. So that actually mathematically we cannot get mathematically perfect loss function for VAE, but we can make a bound. That is the reason why we have bound. Evidence lower bound. K divergence is positive, and then we need to maximize this one. But then K divergence is positive, so that this one becomes. So then let's say we choose to make it lower bound, right? So encoder's output Q should match PZ, and KR is positive. This one is positive. So we can drop it to get a lower bound on likelihood, right? This is positive. At the worst case, this might be 0, right? In good case, this might be some positive value, right? So that in any case, we can get lower bound of our PX, right? Lower bound is making this one to 0, right? The PX is always should be equal or larger than this one. Let me change the color. Okay. So this one becomes lower bound of our target. We'd like to maximize this one. Our goal is maximizing this one, but this one is positive. We cannot get this accurately, perfectly, but we know this is positive. So that in worst case, this might be 0. In good case, this might be some positive number, so that we can get lower bound of P theta x. Lower bound is this one, right? Lower bound, it is minimal when this one is 0. I mean, so that we can get lower bound. And then, okay. So as I said, Px is equal or larger than this one, the first two one, right? So this is our training objective. We'd like to maximize this one. We'd like to maximize the lower bound. That is the training objective of VAE. Because we cannot get this one, let's skip this. But as long as we maximize this one, the lower bound of P prior distribution might be bigger, and then we can maximize this one as well. That is the elbow. That is called elbow, evidence lower bound. As we cannot get this, maybe we can skip this, but we know this is positive, so that let's at least we'd like to maximize this one. Then lower bound of our training objective becomes better. So that is the basic idea of training of VAE, where maximizing this one is minimizing L2 distance, maximum likelihood, right? So minimizing loss from L2 distance between reconstructed data and input data, that is the first one. And maximizing this one means minimizing K divergence, right? Because we have negative sign. So minimizing K divergence between encoder's output and normal Gaussian distribution, that is the second loss function. So there are two things in VAE training. So evidence lower bound elbow, and then we'd like to maximize this one, maximize likelihood, and then minimize K divergence. In practice, we run input data through encoder to get distribution. The encoder outputs mu and variance, and then we compute prior loss, right? We have encoder's output, and then we can compute K divergence between encoder's output and normal Gaussian distribution. That is this loss function. And sample Z, that is differentiable sampling that I introduced in an earlier slide. From mean, this is estimated mean, and this is estimated variance. And the epsilon is just a random scalar, random vector from normal Gaussian distribution. And then this is called reparameterization trick. In this way, we can differentiably sample some vector, something from latent space. We have estimated mu, estimated sigma, and then from this one we randomly sample epsilon, and then we can randomly sample z in a differentiable way. Because this element-wise multiplication, element-wise summation, they are differentiable operator, right? So the gradient can backpropagate to mu and sigma. This is reparameterization trick. And then we can run z through a decoder. Now we have sample z, right? And then we can pass z to the decoder to get p theta x and z. That is the Gaussian distribution, where mean is mu x z and standard deviation is sigma square. And here we have the first loss function, reconstruction loss, maximizing likelihood, and that means minimizing L2 distance between reconstructed output and input data. That is reconstruction loss. So that we compare the reconstructed data and x to be as close as possible. That is the reconstruction loss. Here, reconstruction loss, predicted mean should match x in L2. So mu xc and x should be the same. That is the reconstruction loss. And as I said, this one is computed on this side. We calculate K divergence between our estimated Gaussian distribution and normal Gaussian distribution, so that we can make Z follow normal Gaussian distribution. So here, right, reconstruction loss and prior loss. And once we train it, then actually we do not need encoder. Once we train it, then we remove encoder, and then in the training stage, prior loss. During the training, we make Z follow normal Gaussian distribution, right? So we assume Z roughly follow normal Gaussian distribution. Then after training, we can randomly sample Z from normal Gaussian distribution, right? That was impossible in autoencoder. That was impossible in non-variational autoencoder. But in variational autoencoder, we can sample Z from normal Gaussian distribution as we trained our VAE with the second loss function, prior loss function, which make Z follow normal Gaussian distribution, so that we can randomly sample Z from normal Gaussian distribution after training, and then we can pass it to decoder, simply pass to decoder, and then we can get this kind of images. So once we train it, we can remove encoder, and then we can just use randomly sample Z and then pass it to decoder, and then we can get image. That was, as I said, impossible in autoencoder, non-variational autoencoder, because we do not know random distribution of Z, so that there is no way to properly sample Z. But in variational autoencoder, we know distribution of Z, so that we can randomly sample Z after training, and then we can pass randomly sample Z to the decoder to get randomly sampled images. This is unconditional generative model, right? There is no condition. There is no condition, but in decoder side, maybe we can add like maybe text prompt, text feature to this one, or some other features. Maybe we can use other feature as a condition on the decoder side. This picture only shows unconditional, but for conditional purpose, you can provide text or any conditional information to the decoder side during the training, of course, during the training and testing as well, so that we can train conditional VAE, that is called CVAE, conditional VAE. And this shows the sampled images. As I said, we randomly sample Z1 from normal Gaussian distribution, Z2 from normal Gaussian distribution, and then pass them to the and then we can just linearly interpolate them, and then we can just pass them to decoder, and then we can get this kind of images. And then, so good point is that the variational autoencoder, good point is that training is very stable, very easy to train, not very difficult actually. In particular, there's no adversarial instability. We will learn adversarially training in next class. Training is very stable and easy. Fast inference by encoder and decoder. Especially when generating something, we only need to randomly sample Z and then simply pass the decoder in just a single inference, single forward pass, that's enough. But these days, diffusion-based models, they simply say, repeat, iteratively do this. From random sample Z, they recover something, and then they make this to noise, recover noise decoder, noise decoder, noise decoder. These days, diffusion models do this one very iteratively. That makes really slow. But VAE, they do this only once, really fast, and continuous latent space, enable smooth interpolation, provide uncertainty through probability modeling. But limitation is that, as you can see from this image, latent space is not very expressive. Images, as you can see, is a little bit blurry. So the good point is very stable, fast, practical, but the limitation is that expressiveness, a little bit limited. There can be possible reasons. The first one is encoder is learnable. We from raw data X, we use encoder to squash them to the normal Gaussian distribution, right? We have encoder. To estimate some mu and sigma from input image, right? We try to squash input image to a normal Gaussian distribution. That is the one possible reason, because Gaussian diffusion model, they do not have encoder. Diffusion model have encoder, but it is not learnable. So the biggest difference is that they do not have encoder, learnable encoder. But the Gaussian diffusion model provides very sharp images. So maybe encoder might be one of the reason, and KL regularizer. Gaussian diffusion model, as they do not have encoder, they do not need to compute loss function and the encoder's output, as they do not have encoder. So that they do not have KL regularizers, but VAE as encoder is learnable. So we need to do something on the encoder's output, which is K divergence between estimated distribution and normal Gaussian distribution. So both things are actually about encoder side. Gaussian diffusion model, they do not have encoder, but VAE, it has encoder, a little encoder, and that we need to make encoder properly working. so that we introduce like a K divergence as a prior loss. That might introduce this kind of low expressiveness, I think, because decoder side, GAN, diffusion, VA, more or less similar. But they're also a good point. Very fast and stable.